In this video, we're going to look at an overview of what we did this entire semester. So of course, all the procedures we learned in Stats 2 were examples of inferential statistics. We had problems that dealt with one population, two populations, three or more populations, and then we had this special procedure here that didn't really fit into either of those or any of those three categories. Let's start with the one population case. We wanted to either estimate the mean or the proportion. Estimating the mean is an example of estimating the location parameter, in other words, where the distribution is centered. If I click that, I can see that we had the one sample z-test. That was when we had one group of data where the sample size was large. Then we have one sample t-test. That's one group of data where the sample size is small. And then we had the non-parametric version of those procedures. We had the sign test, and that was basically looking at where the median was located. So remember, these two assume normality where the sign test does not. And then, of course, we estimated the proportion, and with the proportion problems, we had one set of data, and we were conducting the one proportion z-test in those problems. Okay, so that's the scenario for one population. That would have consisted of essentially chapters 7 and 8, and of course, when it comes to hypothesis testing, which is what we're talking about here, that was mainly chapter 8. All right, now looking in chapter 9, basically, where we talked about two populations, we had problems where we had two independent groups of data, and we wanted to talk about where the means were located for those two groups. We had two dependent populations, so that was like the before-after setup, the matched pairs scenario. Then we had two population proportions that we wanted to compare, and then finally, at the end of chapter 9, we compared two population variances. For the comparing two independent populations, there was the independent t-test, and there was also the large independent z-test, but I left that out here because basically the t-test is essentially the same thing, but small sample size. Wilcoxon rank sum test was the test we used as a replacement for that if we couldn't assume normality. So remember, both of these, the Wilcoxon rank sum and the independent t-test, deal with comparing the location parameter, or in other words, the mean or median, for two independent populations. All right. From there, let's look at the next one, which is dependent case. We had the matched pairs t-test, and we had the Wilcoxon sign rank test, right? So of course, dependent matched paired t-test, that procedure assumed normality, and the other one, the Wilcoxon sign rank test, did not. Now, comparing two population proportions, we had the two proportion z-test, and then to compare the two population variances, remember that was the f-test that we conducted. All right, let's take a look now at the third scenario, which is where you have three or more populations. So for three or more populations, we had scenarios where we had three or more independent populations, three or more dependent populations, and then three or more population proportions, right? So for the problems where we wanted to compare independent means, we had the Anova completely randomized design procedure. We also have the Kruskal-Wallis H-test, which was the non-parametric version of Anova CRD. So they're equivalent, except for with the Kruskal-Wallis, you're saying that all the medians are the same, and the Anova CRD, you're saying all the means are the same, right? And the Anova requires the normality assumption, where the Kruskal-Wallis does not. For the dependent case, we have Anova randomized block design that we learned. That was where we had blocks, and that's where the dependency came in. With the Friedman FR test, that's the non-parametric version of the Anova RBD. So if you wanted to perform the randomized block design experiment, but you couldn't assume normality, you would choose the Friedman FR test as a replacement for that. Now, lastly, we learned in that section, or sorry, not in that section, but later on we learned in chapter 13, the chi-squared test for a one-way table, and that allowed us to compare multiple proportions, where we could say proportion 1 is equal to proportion 2 is equal to proportion 3, etc. So that was the chi-squared test for a one-way table. This is also called the goodness of fit test. All right, now from there, last thing we want to look at, test that doesn't fit neatly into any of those categories, which is the chi-squared test for independence. We use that to determine if two categorical variables were independent or not. One example, we looked at heart disease and drinking habits, for example. Okay. So let's talk about a couple of little things here. One little mention here, something that was commonly missed on the test is that if you're looking at the f-test and you're looking at comparing two independent groups, remember that the f-test was often very similar looking in the setup as comparing two independent groups of data. So in both cases, you have two little groups of data where you have n's or sample sizes for both groups, you have sample means for both groups, you have sample standard deviations for both groups. But with the f-test, the problem will say that you want to compare the variances. So that's subtle. You want to be careful, be on the lookout for that. Whereas with the independent t-test, you want to compare the means. So watch out for that if I ask you a question that says, we have these two independent groups of data, and we want to compare the variances for the two groups. You need to be careful and say that we're looking to conduct the f-test in that scenario, whereas it'll look exactly the same visually, except for the problem will say we want to compare the means when it's the independent t-test. So be on the lookout for that. Don't forget also that when you were working with procedures that involve the independent t-test, we had to consider the cases where you had equal variances or unequal variances. So there are some problems where you assume the variances were the same and some problems where you assume they were different. Remember, when you assume they're the same, you're conducting the pooled independent t-test. And when you're doing the scenario where you assume they're different, you have that Welch-Satherthwaite approximation approach that we used. All right, so be aware of those things. The other thing you want to be able to do is to make connections between the procedures that we learned to sort of figure out what's similar about them. So for example, if I asked you which procedures are more powerful, for example, we know that the larger sample size is always going to be a more powerful test than a smaller sample size. All right, so if you're looking for the power of these procedures, for example, a one sample z-test is going to be more powerful than a one sample t-test because the sample size is larger for the z-test, right? So a larger sample size means a more powerful procedure. Only slightly more powerful, though, because these are actually pretty close in power, but the difference here being that the z-test is going to have a larger sample size. Where the sign test is a non-parametric procedure, and we know that non-parametric procedures generally are less powerful than parametric versions. So this would be the weakest, this would be the next weakest, and this would be the most powerful. Or in other words, most powerful, next most powerful, and least powerful among the three groups. Make sure you could rank them in order based on that logic, right? So larger sample size means more powerful, and of course, parametric procedures are more powerful than non-parametric procedures. All right. Other thing you want to do is make connections between procedures in terms of, what they're intended to be used for and how they're similar in that regard. Like, for example, when I look at independent groups here, we know that the independent t-test is similar to the Wilcoxon rank sum test. They handle the same kind of data. And we know that this procedure, or these procedures, the dependent match pairs t-test is related to the Wilcoxon sign ring test, right? This is just the non-parametric version of this one. So I've asked you a question where I said, the independent t-test is to the Wilcoxon rank sum test as the dependent t-test is to the, you would want to answer Wilcoxon sign rank test because that's its replacement. For example, if I said that the Anova CRD procedure, right? So the Anova CRD procedure is to the Kruskal-Wallis H-test as the Anova randomized block design procedure is to the, you'd want to say Friedman FR test, because Anova CRD goes with Kruskal-Wallis just like Anova RBD goes with Friedman FR. They're the same procedure essentially, but this one is a parametric version and this is the non-parametric version. So, they're used for the same kinds of data. If I asked you, for example, on the test, what test involved dependent procedures or dependent sets of data, or used blocking in some way to block out undesired effects, you would think about, well, what procedures did we learn that had blocking? Well, there were certainly two major ones that you would come to mind probably, and that is going to be the match paired t-test. And that's for dependent samples. So you'd say, okay, the match paired t-test is going to be a procedure that used blocking. So did the Wilcoxon sign rank test, and then remember that we had the Anova RBD that also used blocking. So we have the dependent scenario for Anova, and we have the Friedman FR test that goes with that. So there are two major procedures, basically the match paired t-test and the Anova randomized block design test, and then we have their non-parametric counterparts. So we have the Friedman FR test and of course the Wilcoxon signed rank test that does that as well. So either way, those are the kinds of things we're looking for you to be able to do, make connections and to be able to understand when procedures are needed, when they are used. So, if I want to compare 3 or more populations, I know that I have to be using a procedure here. If it's 3 or more proportions, then of course it's going to be the chi-squared goodness of fit test, or the chi-squared test for a one-way table. If it's going to be a situation where I want to compare 3 or more population means, then we're looking at either the Anova procedure, or the Kruskal-Wallis procedure, or the Friedman FR test, or the randomized block design Anova, and then the detail, whether it's dependent or independent, would have to come in to make that decision. So either way, ultimately you want to be able to kind of use this structure, this idea of, there are 1 population problems we learned, 2 population problems we learned, 3 population problems we learned. We learned things that were parametric, we learned things that were non-parametric, we learned things that dealt with independent samples, we learned things that dealt with dependent samples. We learned things that were powerful, procedures that were powerful, and then procedures that were less powerful. We want to make sure we have all that in our minds so that if I ask you to make comparisons between procedures, or if I ask you when you should use a procedure, you have that sort of in your mind and you can make a decision among a list of multiple choice options, right? So at least you'll have the multiple choice answer choices to go through, and you'll be able to sort of check off what fits and what doesn't fit. Okay, so hopefully that helps. The other thing I want to mention is that don't forget, at our webpage we have a link to a review there. So I'm just going to pull that up now quickly. So don't forget, there's this little link for the final review, which we didn't really talk about in class, but you have essentially some problems that you can look at in the homework. The ones that have asterisks here just say those problems have calculations, so ignore the calculation part and just go for the interpretation part. And then you have some follow-up questions here to go over. So for example, it says, which methods used with 1 sample of data? Which methods were used with 1 sample of data? Z-test, t-test, sign test, 1 proportion z-test, right? Which methods are used with 2 samples of data? Well, independent t-test, dependent t-test, 2 proportion z-test. Then you had the f-test, the compare variances, the Wilcoxon rank sum, and the Wilcoxon sign ranked, which are just the non-parametric versions of these procedures, right? Then finally you have which of the above are for independent samples. So think about which tests involved independent samples. Which ones dealt with 3 or more samples. Try to make these connections and try to group things in that way. That way you see the similarities and the differences between tests, right? So look at these methods that deal with 3 or more samples, for example. All the Anova procedures, the Kruskal-Wallis, the Friedman FR, the chi-squared test for a one-way table. What's similar about these procedures? Well, we know that Anova CRD and Kruskal-Wallis both deal with independent samples. Anova RBD and the Friedman FR deal with dependent samples. And chi-squared doesn't really fit with any of those because it deals with proportions, right? And then what methods deal with proportions? Well, 1 proportion z-test, 2 proportion z-test, and then the chi-squared test for a one-way table. So they're connected, right? It's like basically 1, 2, and then 3 or more, right? And then it says, do you see what is similar about the list above for proportions and the one below? So if you look up here, it's 1 proportion z-test, 2 proportion z-test, and then the chi-squared test is 3 or more proportions. Then you have the t-test, the independent t-test, and the Anova completely randomized design. Well, think about that. The t-test, of course, is for 1 population. The independent t-test is for 2, and Anova CRD is for 3 or more. And of course, they're all independent samples, right? Okay, and then it says try this one. The independent t-test is to the matched paired t-test as the Anova CRD is to. Well, think about this. What's the connection between independent t-test and matched paired t-test? Well, they both involve 2 groups of data, right? They're both 2 sets of data, but this one has independent sets of data and this one has dependent sets of data. Well, Anova CRD is for 3 or more sets of data, so we'd want to find something that's also 3 or more sets of data, but goes from being independent like Anova CRD is to something that's dependent. And of course that would be the Anova randomized block design, because that deals with dependent samples. And then we have one more down here. It says, a researcher wants to know if the proportion of BMW owners who are male is higher than the proportion of BMW owners who are female. It says, which procedure have we learned to test this kind of hypothesis? Well, if you think about this, it's a proportion problem, right? So that's key. And if you notice, it's talking about comparing males and females. That's 2 groups, but we're talking about proportions. So again, it's going to be the 2 proportion z-test. So that's good. And if you're using Stat Professor, there are some videos here that I referenced that you might want to look at just to give you just ideas of what topics you need to know. But essentially, if you go through all the examples here that I gave you, you should be able to do the exact same things that are accomplished in those videos.